Thank you. So I was asked to talk about soil characterization here today. I'm here as a practitioner of soil investigations as a brownfield focused consultant. A lot of this work we're implementing on sites, and it's based on, my background is in geomorphic geology, structure, sedimentology, that sort of thing. So I wanted to, let's see here, why is it not advancing? Very case studies on the ISM technique, specifically with some lessons learned. Okay, so it wouldn't be a NUMOA workshop without a long dead European scientist. So here we go. We have Johannes Walther here. He came up with Walther's law, or the law of facies, which you can read for yourself, but it basically describes that in a depositional environment, you have sections of sediments that are laying in series, and over both a horizontal distribution of a site and vertically of the site, you're going to encounter those facies as you're doing your work. So you might have coarse sands 20 feet that way. It doesn't mean that they're just there. They could be right under your feet. And so that variability is accounted for in Walther's law. Here is an image that's directly out of my Sedimentology 201 textbook when I was an undergrad. It's just of a point bar, and it shows you some of this heterogeneity that we're talking about. We have, we have a cut bank on the far right-hand side of that image, and we have our point bar on the left, and the variation that is within that terrain is profound. We have gravels, coarse gravels, and then all the way ranging up to silts within the same environment over very short distances. And horizontally, that is very apparent looking at it in map view, and in vertical view, you have the same, if not even greater, variability in shorter distances, obviously. This probably looks familiar to a lot of you. This is, a typical cross section you see in a lot of reports. And I think I probably could have picked this right out of a Superfund CSM that we were reviewing for a certain site in Vermont that Ryan will be talking about further later. But we have, this section has till on the bottom, sand in the middle, silt on the closer to the surface, and then we have a cap of fill. And so my point is that the variability that exists in each one of these matrices is profound, and you need to pay attention to the very high resolution. So here we have a picture of some till. This till could vary between an ablation till, where it's very coarse with not a lot of fines, to a basal till where that's very rich in fines, but also might have fractures in it. So we often think about tills being confining layers, and it's not necessarily so. We have sand. Is it a climbing ripple? Is it more of a point bar, cross braided stream channel setting? Who knows? You have to have this in your CSM. Up top, one of my favorites, the barbs. If you're in Glacial Lake Hitchcock, you know what I'm talking about. Those are just annual layers within Glacial Lake. And so you have these interbedded silts and fine grained sands, or even silts and clays, depending on where you are in a system. And then fill, this is a picture of a site in Rutland, Vermont, or fill materials in Rutland, Vermont. And this is completely hodgepodge, can be anything. And so within each one of these, having a sense of scale and a tool that's good for sampling to that scale is imperative. So getting back to this, So once we have a sense of the variability that happens naturally, start layering on, what happens when man makes their mark, or humans make their mark on a site. This site is about a half-mile upriver from my office in Montpelier. This is the Capital City gas plant. It's a manufactured gas plant. And you can see that this image isn't all that different from the prior, from the drawing, from the textbook. You have a point bar system with a cut bank. And now you have on this point bar system, you have a manufactured gas plant and all the release mechanisms that are associated with the MGP site. So let's see here. Here's it in plan view. So you can see some of the variations. Some of the things that are inherent on this is a Samware map from, I think, 1926. You have the gasometers here, which were in the prior image, were those snare drum looking things that are used to pressurize the gas to push it around town. Those are obviously oftentimes sources of releases. There's this great little rectangle here, and it's labeled tar well. Like, oh man, you gotta be looking at that. So, so vertical variability, getting into the direct push aspects here. So we have direct push techniques, and primarily there's 3 different types for soil coring. You have macrocores, which are just open cores, open samplers. You have closed piston tools, which can be used as part of the macrocore, and you have dual tube. I brought an example of a closed piston system today. This is what's called an LB system. It's manufactured by Geoprobe, and it's made for it's suitable for being advanced by just like a driving hammer. It's not, you don't need a rig to do this. You can do this with just a 45-pound slide hammer. So this is an example. The Macrocore is probably one of the first direct pushed sampling tools that was used. It does not have, in and of itself, does not have a way to close the piston. So it's just an open tube that you hammer into the ground, extract the tooling out of the ground, and pull it out in an acetate sleeve. If you're going back into the ground in the same hole and you're doing a successive run, you're subject to getting slough going into that annulus, and you could get it in there, and you have to be able to distinguish between the slough and the natural sediment that you're sampling. So the closed piston eliminates that. So you close off the piston and then put that down to where you left off, and you can keep going. And these systems can actually be driven in a way that if you're not interested in the first 15 feet of a core, for instance, you can just drive them closed all the way to where you want to start sampling and then open them up and go. So they're great. The dual tube, I'm not sure if Seth's talk mentioned this because I was out of the room, but the dual tube system is advancing both the sampler and an outer casing at the same time. And they come in various diameters, ranging from 2 inches up to 6. So depending on how big of a core you need, that's what you can select. Obviously, when you go to a bigger number, you go to 6 inches, you need a bigger rig. If you start to get into that, you're going to be using an 8 series Geoprobe or one of the 32 series Geoprobes. So you need a big rig, a lot of down pressure, big hammer. But I have a couple of things here. If you're doing a sampling plan, you might have these many jars to fill up, right? So you have your VOC jars. You have, this might be for waste characteristics if you're doing something that a landfill needs or disposal facility needs. So it's an 8-ounce amber jar for the folks on the phone, and then a 4-ounce jar. This is often for metals, PCBs, SVOCs, etc. And so you need to select, if you're doing the sampling with this, when it's 9/16 of an inch diameter, and you're trying to get from a very discrete interval, obviously you're not going to have enough volume to fill the jar. So you got to select a tool that's appropriate for the volume you're trying to get, because you don't want to have to go down with another run to get more volume. That'd be very time consuming. Okay, next up. Direct sensing. So there are several ways you can assess stratigraphy by not sampling soil. Electrical conductivity, Seth mentioned already. The hydraulic conductivity profiling using the Waterlay PS or the Geoprobe system are 2 kind of often deployed technologies nowadays. And then the cone penetrometer. As Seth mentioned, the EC, electrical conductivity, it doesn't work everywhere. It relies on a dipole, so sending electric current between a dipole on the probe. And in New England anyway, you have a lot of fine materials that are generated from feldspars and quartz. And so these glacially derived fine-grained sediments, the mineralogy variance between that derived silt and clay versus like a phyllosilicate silt and clay is very different. There's a lot more iron, obviously, in the phyllosilicate, so they generate a lot more EC signals. So you see a lot more variations when you have a clay mineral clay versus a glacially derived clay. All right, then traditional sampling, split spoon and thin wall sampling or Shelby tube sampling. These are primarily in the geotech industry. Luckily, not a lot of us are doing split spoon sampling these days. It's very slow, can be dangerous depending on what you're using for a hammer. So we're going to focus on that a little bit more. And we talked about this already a little bit. The Macrocore, in direct push in general, we all know that one of the major benefits of it is that there's low amounts of IDW, investigation derived waste. So you're not generating drums of cuttings as you're advancing a hollow stem auger into the ground. You know, you're producing maybe half a bucket of cuttings from a soil core. Again, we already mentioned that closed, the open borehole is not an issue, or is an issue with the Macrocore. Closed piston takes care of that. It can be slow because you are extracting all of tooling each time out of the ground. So with the closed system, you're tripping it in, going all the way back down. You have to clamp it so you don't lose it down the open annulus, and that's happened before, I can tell you that. But it does minimize cross contamination and slough. So it's a very high quality sample. The dual tube, it does have a few limitations for both penetration and in certain geologies, like running sands, expanding clays. You can have this hydrostatic pressure that forces the sediment into the casing, and then you're hosed. You got to pull things back out. But it also allows, if it is successful given your stratigraphy, it allows for construction and monitoring wells in one push. So you can take your core and then figure out where you want to set your well and target that zone specifically. So it's handy in that way. So some considerations on the analytes. So for VOCs, I was going to set up a little experiment where I had a core and timed it. And so a core comes off the rig, your driller might rip open that acetate for you, and they lay it on the table, top's right, and you're set to log it. You know, a lot of work plans, you have a PID and a box full of Ziploc bags, and you take your screening samples and you let them equilibrate for a bit and screen them after a few minutes. And in the meantime, you're logging all the stratigraphy in that core. But you're out in the sun, you're out in the heat, you have wind, you have an open core. So a lot of this mass is leaving your core. And so it's subject to having a low bias for that result. So it might be 5-10 minutes before you get to that. So the other consideration is that when you have a drilling company that's on a footage rate, or sometimes just want to get home to see their girlfriends, there's an inherent productivity incentive for those guys. They're wanting to push it in as fast as they can and load you up with cores. So if you have 8 cores to log while they're just throwing them at you, they have 2 folks on the rig and you're there by yourself, it's not a good situation for quality. You can lose mass that way. The poor water will drain right out of those cores and you lose a lot of mass. So having a good dialogue between your geologist and your driller and say, we're not here to make 200 feet of coring today. We're here to do this in a quality manner. So having like no more cores coming at you than what you can actually log. So obviously you don't want to be waiting for the driller to bring you a log, but a good driller will be looking at you and knowing that you're ready for another core and having constant communication so you can have, the next core's coming in, you're right there for it. So the other thing, if you're really interested in how much mass is in the soil, for VOCs, I recommend using one of these. This is just a little hole saw. You can get these at any hardware store around. And using a cordless drill, just drill right through the acetate sleeve, clean off a little bit of the layer, and take your syringed plunger of soil right then and there, without going through that logging step first. You can go and take your intervals at set intervals, maybe every foot, or if you have a discrete interval of interest, you're taking it right then and there. So you don't have loss of mass, and you get that extraction process started, and those VOCs are locked in that sample. And then you can open up that core and do your logging. And if you need to hold some of the vials back from the lab because you don't need to analyze that interval, methanol is cheap. The vials are cheap. You can get a box of BOAs produced by the lab for probably not much more than your samples are anyway. So that's something to consider. So decon procedures. Oftentimes I've seen drillers that just, they take out one acetate and they put in another, put the cutting shoe back on, and put it right on the drill rig to be used again. There are components of the system that are touching the soil. If you're going through a hot zone and you have that cutting shoe or the inside of the core barrel, those things should be washed out. I mean, if they're showing up and they don't have any kind of method for decontamination, ding dang problem. You gotta be aware of that. Field duplicates. Obviously we have high variability over a very short vertical interval. So if you have to fill 2 VOAs and you have this tiny little plunger, you're not going to go, vertically. That would be problematic. You want to try to mimic the same structure. I mean, oftentimes in a soil matrix, it's a 50% RPD is the acceptance criteria for a lot of QAPs that I've seen. And we've had problems even hitting that if you don't have a good sampling plan set up. And if you're talking, non-volatiles, you want to make sure that that matrix is very well sampled or very well homogenized before you start putting it in the jar. Okay. Some take-home messages on the vertical distribution and vertical characterization. As Seth mentioned, trying to pair the hard analytical sample, the cost that's associated with that, with some of these more high-resolution techniques, these like the MIP, UVOs, and some of the other direct push methods is a great idea. The image that was on there from the Pine Street site, that is imperative. You need to have representative samples to go to the lab, usually for an EPH method or a PAH method, so you can try to start to see what these things are in the soil. But having the ability to target intervals for soil coring, for those characterization based on a quick technique, something that's doing 200 feet a day of drilling, and you can go back and fill in the gaps with concentration data, it's great. And then selecting an appropriate tool based on what your data quality objectives are for the site and the conditions of the site. If you have gravel, you're not going to go at it with this because you won't get any sample in your core. This is 9/16 of an inch outer diameter of the sleeve. You're just not going to do it. You're not going to get any sample. So you got to go wider. You got to come up with another way to go about it. So surface soil assessment, in my paraphrasing, the Blake quote that Seth is fond of, how many samples are enough? It's n+1. You don't know until you've had one more. So we know that there are problems with compositing, the typical taking a few discrete samples and combining them together and having that value be applied to this area is kind of garbage. You marginally increase spatial representation, but you obviously are decreasing resolution. So, and then a lot of the regulators, certainly Vermont, and I know others, are not in favor, they won't accept compositing data. Compositing, is compositing ever okay? I mean, I actually would say yes, but it's only, in my mind, to get this sample, the one that goes to the landfill. If you have a stockpile and you need to characterize the soil to go for a landfill. Yeah.
Any sample greater than a grain of sand is a composite. So, what's your interpretation of what's a graph and what's a composite? Where you go?
that question for the.
Sure. So the question was, the statement was any sample that's bigger than a grain of sand is a composite. And what makes it for a composite versus a grab? It's, if you can assign it to a discrete point in space, I would call that a grab. Even if it is a jar, it's still a grab. But it is, that's why this is here. so this is one of my archive samples that we don't need anymore. This came from a site in Vermont. And we'll talk about this in a bit when we get into the ISM. But a lab always asks you for non-volatiles, will ask you to fill up a whole jar, sometimes two, depending on the lab. And they're going to open this up and they're going to take a few grams. They have 4 ounces, so 120 or something grams of soil, and they need like 15, right? And so they open this up and they take it right off the top and they put that into their extraction process, and off you go. But what that's like you said, it's a composite. That certainly represents more. And what does that value actually represent? So it is a good question. Okay, so the ISM. So as Ryan mentioned, it's a structured compositing methodology that addresses the inherent heterogeneity of the soil. That's from ITRC. It relies very heavily on upfront systematic planning and to mesh the objectives of the study, the data quality objectives, the objectives of the developer, if it's a brownfield site, for instance, the CSM, both the depositional system and what the analytes of concern are and where they were used on a site, and the method, the actual collection method. Without that systematic planning, it doesn't work. And you need to have buy-in from both the user of the data, not just us, but the client, the regulator, and everybody else. You need to have buy-in from the beginning on how to set up these decision units, what the data mean, how they're going to be used, etc. So you've already seen this figure. This is the out of the ITRC's 2012 guidance, and it just describes the different steps. As I said, I'm the practitioner. I've got the cookie tray and some of the other tools that we use. So what this represents, every one of those shapes represents an actual discrete sample that was collected. There's 30, I think, 30 more. It's a square though. Yeah, 6 by, there's more than 30, but it doesn't matter. Usually it's between 30 and 100 actual grids that you take between 3 and 5 discrete samples from every one of those squares. And we'll go into detail further on that. So all the X's are collected, sometimes using a tool like this. This is just a very easily commercially available push probe. You can find these at Forestry Supply for I think like $80. Just a little push probe, and you put them in. And we'll have as many of these as we have increments. So we'll have one for the X's, one for the O's, one. So we'll just go around and we push it in, and you bring them, you dump the soil in your tray. All the X's go in one tray, all the O's go in another tray, all the triangles go in another. So, one of the things that's kind of nice about this method is that if you have standalone tools, there's actually no decon. You have to do it between decision units, but you don't need to. If you have the right amount of tools for the number of increments, you don't have to decon between these samples because you're compositing it anyway. Okay, so those the soil goes in the pan. The pan gets mixed like crazy, and then you take a grid. You apply a grid to the pan, and you take samples from the pan using a flat tipped scoop of some sort to gain the entire thickness of the sample, because by shaking it and mixing it, you're going to get stratification of that sample, of that soil in the pan. So either depending on the density of the grains, it could be all the coarse stuff's at the bottom and all the fine stuff's at the top, or vice versa. So you want to make sure you collect all of it and weigh it out. Make sure you're taking the same amount of mass from every one of those little points before you put it in the jar. So as I said, the lab only needs 15 grams to run PCB analyses, I think. And some of the lab guys can correct me if I'm wrong. And under ISM, how we do it is we have this dialogue with the lab, and we say, how many do you need for this analysis? How many do you need for this analysis? And we add up all those masses, and that's what we give them. We don't give them any more. And we take 2 jars. We give them 2 jars though. So in case they have to run out of dilution, or a jar breaks, they have a spare. But that's it. They don't get another chance. So, sorry. Okay. So at the end, you have this the sample goes to the lab. They run their analyses. They do the aliquot. The analytical result comes back, and you get 3 results. In this situation, there's 3 replicates, so you have 3 results. And then you run either a mean or you do a UCL, upper confidence limit, through a Chebyshev analyses or one of those to develop your upper confidence level or your mean, depending on your regulator. In Vermont, we use UCL. 95% UCL as our value from ISM sampling. So as Ryan stated, this is back to the same site in Montpelier, establishing the decision units is crucial. And the way it was explained to me in one of the lectures I've been to on this, I think it was Jim Rice out of, where is he from? Where's Jim work? Jim. So we have the tagline is that the decision unit needs to have a common history or a common future. So, and I would make the argument that it has to be both, or at least a common history. And without that, it's really hard to get a consistent concentration. So the next slide up. This is how we did this site. Obviously, the north end of this property, up on the upper side of the slide, there were so many points of entry possibilities that using an ISM approach up there was not going to work. So we did 70 borings up on that end of the site to characterize that portion of the site. But we used ISM in this area of the site, this southern area of the site that was largely hasn't been touched. The Sanborn maps and historical area photos said that there's been a gravel drive through it, but there's otherwise has never had any development on it. And then we did so that was what the light blue represents. The light green represents just an ISM a decision unit that's was placed there for assessing any contamination that's coming off the rail line, which forms the western property boundary. So that's how we did it for that site. So for another site, this one's in Burlington, right on Lake Champlain, downtown Burlington. It's a 16.5 acre urban site that is only half developed with buildings. It was a former manufacturer of ovens in Burlington, and they just moved out of that facility last summer and to take up another residence in Essex, Vermont. But the northern half of this site was recreation. That was like where the company had the company ball field and volleyball courts. So it was never used for commercial enterprises. It is next to a couple of really interesting sites, one of which has already been mentioned. The Pine Street Canal Superfund site is right there. That little strip of water that's coming down out of the top, that is the wetland associated with the canal. And the other property that is due east is known as 128 Lakeside, and that was the home of Bell Aviation, Martin Marietta, Lockheed Martin, and General Electric. In successive, not in that order, but that's who's been at that site. The other thing about the site, it's right next to the Burlington bike path. So access, that's one of the attractions to the site, that it had easy recreational access for folks that are coming on the bike path. That's why one of our developer was interested in getting it. But it's also right next to the Burlington Railroad, or the Vermont Rail Line, sorry. So they're trying to redevelop this site as an incubator space, especially the building, this huge manufacturing facility in the bottom, and turning it into a business incubator. The building just north of that for commercial offices and some light manufacturing. And then have more recreational access to the lake, and have it be more of an open environment instead of just like this corporate backyard. It's going to be an open site. Okay, so, and then the last thing is they did want to revise the parking lot. This building here had parking right up against the top of bank going down into the lake. So they wanted to, be a little bit more of a steward of the site, move that parking out of the way so we didn't have all the stormwater running off into the lake, and push it to behind the building so they could have more of a pretty front yard, So this is what we did. And prior work, we got to do prior work first. So there had been work done for a previous prospective purchaser, not our client. They indicated that there were PAHs at various parts of the site, but not much in surface soil. It was at depth and only in very limited areas of the site. They did detect VOCs in soil gas. Those could be a talk later on vapor intrusion investigation. So we did some work to figure out that problem more, but not high concentrations. They're just a little bit higher than residential standards, but not higher than industrial. So it's looking good so far. They did find PCBs and glazing in the windows, but not at the concentrations that you tend to find PCBs and glazing. Usually it's like 20,000 ppm or something like that, and this was not even up to 50 parts per million. So it was so far so good. Groundwater, they had done some groundwater investigation using wells, but had found nothing in groundwater. And as it turns out, this site is somewhat removed from being a down gradient recipient of groundwater from this site, because there's actually a topographic high that runs right along here. And groundwater from this site is actually flowing north towards this wetland. So it doesn't even go that way. Okay. So for our scope, we did some targeted borings to assess where they're planning to do excavation work to install new utilities. We did some superficial and shallow sampling where they're trying to put access to the bike path. And we did a comprehensive building material assessment to get a bigger picture, a better picture on the PCBs and glazing, and a VI assessment, but those things aren't really germane to what we're talking about. The ISM, we did do an ISM unit of this proposed parking lot, which is just to the north. So they were shifting it from south of this odd building here to the north. And we figured it hasn't been used for anything commercially, and it was going to have a common use in the future. So we thought this is ideal for ISM. But then we did the data. So this is we did three replicates for this decision unit, an A, B, and a C. We analyzed for a number of different analytes. The only thing that actually even came back with any detections at all were the carcinogenic PAHs. Lead and arsenic was nothing. So we had some pretty low, greater than the residential standard in Vermont for a few of them, but well below the urban background, which is kind of like what we're looking for. We have a 0.58 milligrams per kilogram of benzoate pyrene T. And we have a soil screening value of 1.54 for industrial sites. So those are the two numbers that are germane to the site. So for the first replicate, we had a TEQ of 0.35, not bad. Second, 0.28, so looking good. Last one, we had a much higher concentration of these others here, bringing us to a TEQ UCL 5.4. So instead of having this like really nice picture to bring home to the client that you're below the standard, it came back as well above industrial. So two similar replicates and one that was an outlier. Here's how we did the sampling, just to kind of get to the point, to the punchline. The three colors, three shapes up here represent the actual individual increment that was collected. So we collected, 20 grams of soil from every triangle that's up there, every blue circle, and every square. So you see that the C replicate is the yellow, the A replicate is the red, and the B is the blue circle. Does anybody have any ideas what happened? Seth, you can't say anything because you were here yesterday.
Well, it's all the yellow ones put together.
So we'll get Here, so those 10 samples are right up against the rail. So those, what my thinking is that those 10 samples skewed the whole set of data. So that's why we had one outlier replicate that made our UCL just go through the roof. So this gets back to systematic planning and having a good understanding of the site. My thing, in wind in Vermont and actually anywhere in New England is usually from the west. So we were thinking like, this wasn't even down. It's Lake Champlain on one side. It's not even a depositional problem. But what my thinking is that this is running off the wash water, or rather the stormwater from the rail is washing off the base material of the rail line and going into this. There's a tiny little wetland that stretches right along this rail. It's a raised rail. So it's washing into that wetland and depositing the pHs there. So they have to move the parking lot anyway for the wetland. And so the story is we're going to confirm this hypothesis and we're going to adjust, and hopefully we'll figure out that we need to put up a fence around the wetland to keep people out, and then the rest of it will come back less than the standard. But this is a site in process, so we don't have like an ending on that one. So that's all I have.
In retrospect, would you have decided in retrospect, would you have preferred to make a decision unit series of cells along the railroad track?
Yeah, and that's what our next step will be, is to actually do a decision unit along the entire eastern edge of the site, right to the west of the rail line, to confirm that hypothesis. So it will be another stacked decision unit right up the site, and there'll be another decision unit. So now we have an exceedance of the industrial standard right next to where folks are going into the lake, recreational users. So we have to confirm or deny whether or not that presents an exposure pathway for those users of the beachfront. So there's kind of a twofold reason to go out there and do some more assessment, but that's one of them.
Okay, other questions? So I will just say we wanted to include incremental sampling methodology that he just sort of went through the results of, because EPA Region 1, when we announced this workshop, emailed me to make sure that we were going to be covering this, because it is an approach that EPA, at least Region 1 and maybe nationally, is really wanting everybody to start understanding and utilizing more, because they believe in it. So I encourage you. It took me a little while to get it straight in my head yesterday, but so I think, because I think the way the samples are collected matters too, and yeah, that your decision unit and figuring out what appropriate decision units are is key. I think one thing that we didn't mention is that it's not just for surface sampling, right? You can say a tiny bit about that.
Sorry, I glanced over that. So we've done ISM even in vertical. We've had, we've done established a grid of 30 by 30, or a grid of 30 squares, and collected the replicates using Macrocores down to 5 feet. So then taking the 0 to 5 interval and taking a individual increment from there, and another one and having all of the 0 to 5 represented as the increments. So on a 30 increment grid, you're taking 90 borings, so it takes a while, but you can get vertical decision unit established that way. So you can have a decision unit that's 0 to 5, at 2 feet, or 4 feet, or whatever. So that can be really helpful if you're doing, an excavation, or if you're planning to do a big brownfield site where they're having to install subbase for a parking lot or whatever. And so you can establish a decision unit vertically that way. And I think it's, you know, it's up to your creativity. I mean, you could do a picket fence decision unit, so it's actually oriented vertically, which would be interesting. I haven't tried that yet, but yeah.
So I think this is somewhat contradictory to the, you know, the regulators don't like composites. It's really a super composite.
Well, there's just so much more of them though. So usually you're doing like 2 or 3 samples or 4 samples for a composite, but you're taking 30 samples, 30 locations and combining it together. It's just much more representation in that sample. So yeah, I mean
Certain things are uniform in your decision. It's more representative.
Yeah, so it just accounts for that. So you do mask if there is a hot spot, you mask it. And oftentimes what can happen is that, you know, you might have a hot spot that's making it so you have to manage a bigger area to a higher standard than you would otherwise. But it's useful for risk because it is, you know, averaging over a wider area. So that's what it's intended to do. And so the ITRC document that's been mentioned a few times has a lot of background information on the statistics that were involved in developing this approach. And I highly recommend it. It's a really long document, but it's very good. So.
Okay, great. Well, thank you again, Dan.